on this on the 5152 reading guide. It says to look at figure 5.7 in the caption underneath it. And that shows you a picture of an endothermic reaction. And this is always tough for students, so I want to talk about this one for a minute before we get into the little activity that we're going to do here. So the question is, if the reaction is endothermic, why is it the temperature goes down? Okay, because if you think about it, endothermic is absorbing energy from the surroundings, right? Wouldn't you think that that would make the temperature go up? It's absorbing energy from the surroundings? Okay, do you guys know what I mean by endo and exothermic?
Yeah.
Okay, so endothermic again, just, well, I guess we got to do this on here. Sorry, HIPAA was violated. No, HIPAA was not violated on that one. That's for PBS. Don't worry about it. So, our beaker, if our beaker is our system, okay, if the energy is going from the system to the surroundings, it's going out, exo, it's exiting, so that's exothermic, right? You're probably going to be able to hear this cough drop on this video, and that's going to be annoying. I have a cough drop, and every time I talk, it's like, I can hear it in my ears, so you're probably going to be able to hear it on the video. So sorry if people are watching this video, if you are. Yeah, but I'm apologizing to future you when you watch this video. So, all right. So, endothermic means that you are putting energy into the system, okay? So now that, I mean, just with that little quick review here, if something is endothermic, energy is going into the system. Why is the temperature going down? If we measure the temperature of an endothermic reaction, why would the temperature be decreasing? Okay. This is really tricky. Really tricky, especially if you've had a biology class where you've talked about this. The biology teachers, and it's not their fault because this is hard, okay? They don't do a good job of talking about this. What they have told you, your biology teachers, is that energy is stored in the chemical bonds, right? And that when those bonds get broken, like in a long carbohydrate, that's how you get energy. That's not really true. Okay? Yeah, and I'm really sorry about that for their lie. They didn't know they were lying, okay? Yeah, these are, well, these are not like my lies. Usually I know when I'm lying to you. Not always, okay? But this one, they just don't know, okay? Or maybe they know and they really don't want to get into the nuances of it. That's probably what it is, to be perfectly honest. I'll give them the benefit of the doubt on that one. What's really happening in those carbohydrates breaking down, you've got a bunch of carbon, hydrogens, oxygens, all that stuff, okay? Now what happens in a hydrolysis reaction that separates the parts of the chain from each other, because basically with, I need to do this as fast as I can here, but so you know, with the carbohydrate, you've got your, is that a pentagon? Yeah. You've got your rings, you know, that are, oh boy, oh boy, oh boy. Got into trouble on that one. All right. Anyway, just pretend those are two pentagons, all right? So basically what you're doing here is you're breaking this apart, okay? You're breaking the macromolecule apart. But what happens when you break this apart is you also form new bonds at the same time, right? So you're breaking this, but then there are new bonds that are also forming. The energy comes from the formation of the new bonds, not from the breaking of the old ones. Okay? Now, think about this. When you've got two magnets that are close to one another, you've got a positive end and a negative end. Actually, I have two magnets here. Okay? So positive end and a negative end, they're connected, right? This is a chemical bond. What do I have to do to get these to come apart? I have to pull them apart. I have to... Sorry.
I didn't even want it.
I have to exert a force, don't I? To pull these apart? You guys see this? To break this bond, I have to provide energy. It takes energy to break chemical bonds. Okay? Now, we're going to talk about this in more detail in later chapters, so I just want you to kind of understand that right now. The energy gets released when these two things come together and a bond is formed. All right? So it is not the breaking of the carbohydrate chain that gives you the energy. It's the new bonds that form on the ends of each of the new chains that gives you the energy. Okay? So that's a much more nuanced discussion of that than you probably had before. But I need you to understand that because everyone always argues with me when I tell them later in the class that energy is stored in the bonds and it gets released when you break the bonds. That's exactly the opposite of what it really truly is. Okay? All right, so let me say this one more time. Energy is released when a bond forms. It takes energy to break a bond. I think that's the easiest way to think about it, right? When you pull a bond apart, it takes energy to do that. So just remember, bond formation is the opposite of that process. Where does the energy come from? Okay, so that's where we're talking about endothermic, right? It can't come from nowhere. I mean, there needs to be an energy source, right? So let's say that this is happening, okay? We have to break this bond. Well, the breaking of this bond is an endothermic process, which means there's some energy, whoops, that's the surrounding, sorry. There's some energy up here, and it flows into the system, okay? So it's getting energy from the surroundings in order for that bond to break. Oh, when you create the bonds, because what's happening is they're coming to a lowest point of potential energy, okay? And again, we'll talk about this more but there's a certain distance between two nuclei that's like the perfect distance, okay? And at that distance, you have the lowest possible potential energy, okay? So maybe you're not going to be able to see this on the video. That has a lot of potential energy, right? You got tape on the side of a table. It's up high, right? So that's a high potential energy state, right? I knocked this off of here. Well, it had some kinetic energy. Now, it's in a much lower state, right? So to go from this higher state, the state of higher potential energy, to a state of much lower potential energy, some kinetic energy got released. Does that make sense? Okay? So that's exactly what's happening here. They're at a higher state of potential energy when they're apart. When they come together, now they have a lower state of potential energy, which must mean that some kinetic energy got released in that process. Okay? It's tricky, I know. This is where physics, biology, and chemistry all sort of combine for a second. Yeah?
Does it have to do with the thing that we talked about with the electrostatic energy levels? Like, it's like a bond, a special sort of energy level that would release energy if you're...
Okay. We're going to talk about molecular orbitals later in the year very briefly, and it's going to be hard because it kind of blows my mind a little bit. So we will talk about how a molecule interacts with light and the electrons jump certain energy levels and how those energy levels change when a bond forms. But for this, let's just think about potential versus kinetic energy. I think that's the easiest way to talk about it. And I know this is tough, okay? I get that. Here's the simplest way that I can put this. And I think this will work for some of you even if you're not following the whole physics discussion right now, because this does get very physics heavy for a minute. Gets very physics heavy. That's what I said. Just think about a thermometer, putting a thermometer into a solution that's reacting, okay? So you've got your thermometer in this endothermic solution, right? And your thermometer is reading, you've got the readings on the thermometer here, okay? And as that doesn't look like a thermometer. I'm sorry, my drawings are horrible. I don't know what that looks like, but... So we dangle a caterpillar into an endothermic reaction, right? Okay. Here's the thing. Is the thermometer part of the system or is it part of the surroundings? Ah, okay. Well, maybe that's helpful because the energy is going to go out from the surroundings to the system, which is going to make the thermometer feel colder. Does that make sense? Okay? So the temperature goes down. if you put your hands on an endothermic reaction, your hands are part of the surroundings, okay? So it's going to take energy from your hands, so your hands will feel colder, okay? So that's endothermic, all right? I think that's probably the easiest way to think about it, but if you like the physics behind it, and I also want you to kind of understand this bond thing, okay? I'm talking way longer than I meant to, but that's a tough one, okay? All right, so let's look at some of these other ones here. The energy diagrams. You know what? I'll let you look at those. We're not really going to cover those until later in the unit, and we're going to do an activity on them, so I don't think I need to really talk about them now. Look at what they're talking about there, though, on the new course description, because that might be worthwhile to at least see how they're describing those. Now, I do want to look at this, though, because their explanation of heat is just better than the book's explanation of heat. So I want you to see this, okay? So that's 5A, 2A. Pull that up real quick. Let's take a guess here. Oh, that wasn't too bad. Why is it doing this again? Why are you doing this to me? I don't understand why this thing keeps not moving when I... Yeah, see, that's not helpful. Alright, I guess I'm going to have to do it this way. Alright, so 5A2. Nope, went too far. Okay, so here's the description of heat that they give in the new AP curriculum. Process of kinetic energy transfer at the particulate scale is referred to in this course as heat transfer. Okay, heat, we're talking about kinetic energy. You need to understand that. Okay, it's the movement of particles. How fast are they moving? Average kinetic energy is temperature. Does it say that here? Oh, well, no, not really. Okay, but I know it says it somewhere. I can't remember exactly where. But average kinetic energy is the same thing as temperature, Kelvin temperature. Okay. So on average, molecules in a warmer body have more kinetic energy than the molecules in a cooler body. All right. Collisions of molecules that are in thermal contact transfer energy. So every time molecules hit one another, they transfer energy just like any two colliding bodies would. Right. So you think about a pool table. You hit the cue ball, hits the other balls, transfers some of its energy. Okay, that's what's happening. Scientists describe this process as energy is transferred as heat. So anytime it says energy is transferred as heat, that's what they're talking about. Okay. Yeah, the Newton cradle. Mm-hmm. Yeah, that's kind of what's happening here. It's transferring its kinetic energy. Okay. Eventually, if you put two things together, something warmer, something colder, the kinetic energy is eventually going to average out, okay, so that you're going to end up with these two things becoming the same temperature, all right? So then we would say that they're at thermal equilibrium at that point, okay? Now, heat is not a substance, okay? It's a flow of energy from a warmer object to a cooler one, all right? So we'll say heat exchange or transfer of energy is heat. So don't say that something contains a certain amount of heat, okay? Sorry, you can't say something's hot anymore. You have to say, boy, that object contains a high amount of kinetic energy in its particles, right? Okay, that's the way you have to say it now. Sorry. And then the transfer of thermal energy, it has to do with specific heat as well. Okay, so we'll kind of get to that one a little bit later. But I just want you to be familiar with the way that we chemically talk about heat and what that really means. We're talking about average kinetic energy. Okay? See if there's anything else in here that I really need to talk about. Work includes all forms of energy other than heat transfer. Yeah, I would look at that. But I'm not going to go over it now because we need to get to the activity. Yeah, we're going to do an activity where we talk about the flow of energy. So I think that'll be fine. We don't need to cover that on here. Okay, chemical energy and thermal energy. I kind of want to look at this one because I think they might give a different definition than the book. And then we'll get going with the activity. That's 5C, enduring understanding. Okay. Oh, here it is. Breaking bonds requires energy, and making bonds releases energy. Okay? So there you go. It's in the AP curriculum. It must be right. Right? So this is long. Okay? So I would take the time to look at this because this does do a good job of describing some of the physics behind it. All right? So what it's saying is these bonds happen because the negatively charged electrons and the positively charged nuclei are attracted to one another. Okay? As they move closer to one another, the potential energy gets lowered, okay, until they reach a point where you've got the lowest possible potential energy. As the potential energy lowers, that must mean that that energy is going somewhere. If it's not potential energy, it's kinetic, right? Okay. So what's happening there as that potential energy gets lowered is that it is changed into kinetic energy, okay? So bond formation is an exothermic process. It releases energy to the surroundings as kinetic energy, okay? So that's how that works. And then the opposite is true for opposing process. To break a chemical bond, again, you have to pull it apart. That takes energy. That requires energy, so that's an endothermic process, okay? See, why is it letting me do it here, but it's not letting, I don't understand. I think that's kind of the main thing that I really wanted you to see on that. Now, where does it even talk about chemical and thermal energy? Okay, here we go, at the bottom. In chemical systems, the stored energy is called chemical energy, and the energy of motion is called thermal energy, okay? So when we're talking about chemistry, you can roughly translate chemical energy into potential energy, okay? And then when we talk about the energy of motion, kinetic energy, we're going to call that thermal energy, okay? So when we talk about heat, we're talking about kinetic energy. When we're talking about chemical energy, then we're talking about potential energy. So I just want you to understand those two distinctions, okay? All right. Hopefully that helps a little bit. There's a lot of kind of heady stuff in these first two sections, and they are hitting this a little bit harder than they have in the previous curriculum. So we need to make sure that we get this because I'm sure they're going to test on it a little bit harder this year. Okay? All right, so that's that. I'll go ahead and stop the video and we'll start on our activity.